You know, when you walk into a store and grab the very last box of cereal off the shelf, you probably don't think twice about it.
Right. You just toss it in your cart and keep walking.
Yeah, exactly. But the second you take that box, an invisible trigger is tripped. Suddenly, these massive gears start turning hundreds, sometimes, thousands of miles away.
All coordinated just to replace that exact box you just walked away with.
Okay, let's unpack this. Today's deep dive is all about the science of keeping the shelves stocked.
It's a huge topic.
It really is. We are decoding the heavy distribution and inventory mechanics that make this happen seamlessly behind the scenes. We've got a comprehensive set of distribution and inventory planning documents as our sources today.
And they are incredibly detailed.
Oh, yeah. So whether you are, prepping for a global logistics meeting or you're just insanely curious about how products magically appear when you need them, we are going to pull back the curtain on supply chain replenishment.
And it really is a brutal machine to operate because you're constantly caught in this high-stakes mathematical tug of war.
A tug of war between what, exactly?
Well, on one side, you have the financial reality of carrying inventory. Every square foot of warehouse space, every forklift, every pallet sitting idle, it just bleeds cash.
Right.
But on the other side, you have the absolute necessity of meeting customer demand. If someone wants a product and your shelf is empty, they don't wait.
No, they just go to a competitor.
Exactly. So everything we are going to explore today exists to help companies survive that specific tug of war.
So let's talk about how companies actually decide to move that inventory around to prevent those empty shelves. Because from the sources, there seem to be two fundamental philosophies at the core of all this.
Push systems and pull systems.
Yeah. And I like to think of a pull system kind of like how I manage my groceries. I look in the fridge, I see the milk is gone, so I, pull the trigger and go to the store to buy more.
You're reacting to the immediate reality in your kitchen.
Right. But a push system, that feels more like signing up for one of those meal delivery subscriptions.
Oh, that's a good way to look at it.
A central planner decides what I'm eating this week based on some algorithm, and they just push the box to my doorstep before I even realize I'm hungry.
The meal kit analogy works really well for the core concept, but let's push a little deeper on the business implications there. Pull systems are inherently decentralized.
Meaning the decisions happen locally.
Yeah, the trigger happens right there at the local warehouse level. A specific distribution center sees its stock drop below a certain safety line, so it places an order to pull more from the factory.
So it's highly responsive to the local physical reality on the ground.
Right.
Which sounds ideal, right?
Yeah.
You only buy what you know you absolutely need based on what's actually selling.
You would think so, but there is a massive blind spot built into that strategy.
What is it?
Because the local warehouse is just reacting independently, the upstream suppliers, the central hubs, and the factories, they have zero visibility into the actual demand building up.
Oh, wow.
Yeah, they don't know a region is having a run on winter coats until they suddenly get hit with this massive order.
They're just flying blind.
Basically. So to protect against that sudden shock, a pull system forces you to carry a much larger buffer of safety stock at every single node in the chain. You end up tying up a ton of working capital just to feel secure.
Oh, I see. Everyone is padding their own secret stash of inventory because they can't see what the rest of the chain is doing.
Exactly. Now, what's fascinating here is how push systems solve that visibility problem by being highly centralized. A planner at corporate looks at the entire network's inventory from a bird's eye view.
No, they see everything all at once.
Yes. Replenishment isn't triggered because a local shelf is empty today. It's triggered because the planner forecasts that a shelf will be empty 3 weeks from now.
Okay, I get it. Because that central hub sees everything, you can run a much leaner operation with lower system-wide safety stock.
Right?
But the obvious catch there is, if your prediction is wrong, you just shipped 10,000 winter coats to Miami in April.
Precisely. Push requires incredibly sophisticated data and forecasting training to work. If your data is bad, you bleed cash on misallocated freight. Yeah. Pull is safer if your data is unpredictable, but it costs you a fortune in holding costs.
So those are the massive structural philosophies. But let's bring it down to the floor of a warehouse on a Tuesday afternoon.
Okay.
How does a local manager actually know it's time to reorder? Do all warehouses use the same rules, or is there like a menu of options depending on how complex your operation is?
There's definitely a menu, and it progresses from very rigid, basic math all the way up to highly dynamic software. The most basic tool in the tactical toolkit is ROPEOQ.
which stands for reorder point and economic order quantity.
You got it. It's low complexity.
Okay, so this operates as a pure pull system then.
Yes, exactly.
Yeah.
The reorder point is your numerical trigger. When your physical inventory drops to, say, 50 units, the system automatically fires off an order.
And the EOQ part.
The economic order quantity dictates the size of that order. It's always a fixed lot size, say exactly 100 units, because someone did the math to figure out the absolute cheapest freight and bulk discount configuration for that specific item.
So it's simple. A fixed trigger and a fixed amount. Trip the wire, send the standard box.
Exactly.
That makes sense. But what if a warehouse doesn't want to rely on an unpredictable volume trigger? What if they want a predictable schedule?
Then they move up the complexity ladder to a base stock system. This replaces the volume trigger with a time trigger.
Okay.
So every Tuesday, you review your stock. If you sold 42 units last week, you order exactly 42 units this Tuesday. You're just topping off the tank to get back to your baseline.
That feels a lot easier to manage from a labor perspective. You know exactly what day the truck is arriving.
It is.
But here's the problem I see with both of those systems. They are completely blind to the future. What happens if my demand isn't a smooth, predictable line?
Right, the lumpy demand problem.
Yeah, like what if I sell 0 units for 3 weeks and then suddenly a customer orders 200?
And that exact vulnerability is why supply chains developed TPOP, which is time-phased order point.
TPOP.
Yeah, it's high complexity. TPOP doesn't just look backward at what you sold or downward at what's physically sitting on the shelf today. It calculates a projected available balance into the future, and crucially, it offsets by lead time.
Okay, offsets by lead time. Break that jargon down for me.
Lead time is just the practical reality of how long it takes for a truck to actually arrive after you click order. Let's say it takes a full week to get a shipment.
Okay, a week.
TPOP looks at your current stock, looks at incoming, confirmed customer orders, and calculates a future reality. It might say, hey, we have plenty of inventory today, but based on incoming orders, we're going to run out next Thursday.
Oh, I see.
So since it takes a week for the truck to get here, we must place the order today.
Oh, wow. So it provides planned shipment data, and it actively integrates actual order data, not just relying on historical averages.
Exactly. It doesn't assume consumption is perfectly constant.
That is incredibly powerful for managing those lumpy, unpredictable sales spikes.
It's a massive leap forward. But if a company wants the absolute gold standard of dynamic adaptability, they use a framework called DDMRP.
Demand-driven MRP.
Right. It's medium complexity to set up, but highly dynamic. Think of DDMRP as establishing a dynamic traffic light system for every single product in your warehouse.
A traffic light system.
Yeah, it relies on daily reviews of buffer priorities based on something called the net flow position.
And what exactly goes into a net flow position?
It takes what you physically have on hand, adds what is currently on a truck heading toward you, and then subtracts your qualified demand.
Qualified demand being actual orders.
Right. Not a vague forecast, real confirmed orders due to ship out immediately. Based on that daily calculation, your inventory falls into a green, yellow, or red zone.
I really like how visual that is. So what do the colors actually dictate to the person running the system?
The green zone dictates the size and timing of your order. It's your target order up to level.
Okay, green is the target.
The yellow zone is your normal operating inventory. It represents the average amount in transit, the stuff you fully expect to consume while waiting for your next shipment.
And the red zone.
Red is your critical safety stock amount. You never want to dip into the red unless there is an absolute emergency. By clearly defining these zones, DDMRP stops people from panicking.
Because without those zones, a warehouse manager might get a massive unexpected order, completely freak out, and order triple the normal amount, which then makes the factory freak out.
Which causes massive disruptions. DDMRP's color zones absorb that shock. It tells the manager, yes, we got a big order, but our net flow is still sitting safely in the yellow zone. Do not panic. Just order the normal green amount.
Okay, so we've established these highly intelligent tactical systems running inside a single warehouse. But large companies don't just have one warehouse, they have dozens.
Sometimes hundreds.
Right. So how do they coordinate all these localized replenishment rules without the different buildings just hoarding inventory and fighting each other?
To manage a network that complex, you need DRP, Distribution Requirements Planning. If the warehouse systems are the local managers, DRP is the centralized brain coordinating all the limbs to make sure inventory flows efficiently.
The central brain.
Okay.
So how does it see the whole map?
It relies on a foundational structure called the Bill of Distribution, or BOD. Picture a massive cascading waterfall.
Yep.
At the very top, you have your central supply.
A factory, essentially.
Right. Product flows down to regional distribution centers, and from those regional centers, it flows further down to satellite DCs that actually serve the customers.
So the physical goods only flow down the chain.
Exactly. But the demand signal has to flow up the chain. The local satellite calculates what it needs using TPOP logic and sends the signal up to the regional hub.
Okay.
The regional hub consolidates all those local signals, figures out what it needs, and sends a massive signal up to central supply.
Let's make this tangible, because trying to visualize the grids for this can get a bit abstract. Imagine a massive apparel drop, a highly anticipated running shoe. We have a central supply in Memphis, and local warehouses, say, warehouse A, B, and C in different cities. How does DRP actually crunch the numbers?
Let's zoom in on warehouse A first. DRP takes inputs like the planning horizon, the item forecast, safety stock, and lead times. It populates a planning grid.
Right.
It starts by looking at warehouse A's gross requirements for the upcoming week. Let's say they need 5,000 pairs of the shoe.
Okay, warehouse A needs 5,000.
Next, DRP checks the scheduled receipts. Are there any trucks already on the way? Let's say no. Then it looks at the projected available balance. This is the current inventory on the shelf. Say they have 1,000 pairs.
So they need 5,000. They have 1,000. They are short 4,000 pairs.
That 4,000 is their net requirement. So the local system generates a planned order release for 4,000 pairs.
Simple enough.
But here is the critical part. If it takes 3 days to truck the shoes from Memphis to warehouse A, DRP tells the system to release the order 3 days early.
Okay, but Memphis is dealing with warehouses B and C at the exact same time.
And this is the magic of DRP grids. Warehouse A's planned order automatically rolls up the waterfall and becomes a gross requirement for Memphis. B's order rolls up, C's order rolls up.
Oh, wow.
Memphis now has a perfectly synchronized view of what the entire system is going to pull.
If we connect this to the bigger picture, it's essentially merging both push and pull features. The DCs place orders, which is a pull, but central supply gets advance notice to suggest order sizes, which is a push.
It really is the best of both worlds.
I want to zero in on a specific input mentioned in the DRP grid, safety stock.
Yes.
Because there's a business strategy you hear about constantly right now. Every company wants to get closer to the consumer for next day shipping. So let's say a company decides to close their one giant warehouse, and they open 2 smaller ones so they're geographically closer. My initial thought is, if I sell 1,000 widgets a month, and I split my massive warehouse into 2 smaller ones, my total safety stock shouldn't change, right? I just cut it in half, 500 here, 500 there.
That is an incredibly intuitive assumption, and it is completely wrong.
Wait, really?
Yes. Adding locations doesn't impact your regular cycle stock much, but your safety stock absolutely rises.
Wait, why? If the national demand is exactly the same, why do I suddenly need more backup inventory?
Because safety stock exists to service unpredictable volatility. When you had everything in one central location, a random spike in sales in one city was probably offset by a slow week in another. The volatility cancels itself out.
Oh, I see. But if the locations are isolated?
Exactly. They have a smaller, more volatile customer base. They don't have the other city's slow week to balance out their spike. This is governed by a brutal mathematical principle from the text called Master's square root law.
Okay, break the formula down for me.
The formula is your future safety stock equals your current safety stock multiplied by the square root of your future DCs divided by your present DCs.
Okay, let's walk through the exact math problem from the source text.
Sure. Imagine your regional safety stock is 500 units in one location. You increase to 2 satellite DCs. You don't just put 250 in each.
Right.
You take 500, multiply it by the square root of 2 over 1, which is just the square root of 2.
Which is like 1.414.
Exactly, 1.414. So you multiply 500 by 1.414, and the result is 707 total units of safety stock.
Wait, total, so per location.
You divide 707 by 2, it's about 354 units of safety stock per satellite DC.
Oh, wow. So your total safety stock just jumped from 500 to roughly 708 units.
Just by adding one building.
So for the listener, the huge takeaway here is that faster order cycle times and more reliability come at the literal cost of holding way more total safety stock across the network.
It forces a really tough strategic conversation.
Which perfectly tees up the final piece of this puzzle. All of this warehouse-level math doesn't happen in a vacuum. The C-suite needs to know what's going on to plan budgets, hire workers, and buy trucks. How does DRP actually talk to the rest of the business?
The calculations in DLT don't just stay in the logistics department. They feed the entire corporate strategy. Specifically, DRP feeds two major linkages.
And what are they?
S&OP, which is Sales and Operations Planning, and Master Scheduling.
I hear S&OP thrown around a lot. What is DRP actually handing over to them?
S&OP looks at the big picture. So DRP provides the product family level channel demand and the overarching logistics resource requirements plan. It tells executives broadly how much product the network will pull.
Okay, so if S&OP is the telescope looking at the big picture, that makes master scheduling the microscope.
That's a perfect way to put it. Master scheduling gets the highly specific item-level channel demand and the localized logistics capacity plan.
And this translates into very real-world requirements, right?
Absolutely. DRP generates incredibly tangible reports. You get inventory investment reports to see costs and balances. You get transportation planning reports for weight and volume.
Pallets and trucks.
Yeah, warehouse space reports for pallets. And my favorite, the labor and equipment reports. It literally tells a manager exactly how many extra forklifts or picker vehicles they need to rent for the holiday rush.
So what does this all mean? It means a single beep of a barcode at a local DC ripples all the way up to the CEO's desk, deciding if they need to lease more forklifts next quarter. The connectivity is just staggering.
It really is an amazing ecosystem.
Well, we have covered a massive amount of ground today. Thank you for joining us on this deep dive.
My pleasure.
We recapped the journey from the philosophies of push and pull, went through the mechanics of ROP and DDMRP, up into the DRP grids, explored the surprising math of the square root law, and finally, out to the corporate S&OP strategy.
And before we sign off, I want to leave you with a final thought to ponder based on that DDMRP logic we discussed.
Oh, would love to hear it.
Think about how you manage your own time or household supplies. Are you operating on a push system, rigidly planning out your weeks regardless of reality? Or are you using a pull system, constantly reacting at the last second?
Oof, definitely reacting sometime.
Right. But what if you applied DDMRP's green, yellow, and red buffer zones to your own life? Setting dynamic order up to levels for your energy, your groceries, or your workload. Stepping back when you hit the yellow zone instead of waiting for the red.
That is a phenomenal way to reframe it. Well, keep questioning the systems around you, and we'll be back soon with another deep dive.